I'm going to take a test-driven approach to building the example of a composite. I'm going to start by creating a JUnit test, and I'm going to call composite test and put it under com.scibike.composite.test. I build this simplest test first, one that tests the constant. And I'm going to write code like if I had already implemented it. I'm going to create an expression that I call E that takes a new constant, and I need a test value, which I'm going to set to 3.0. And then I'll write an assert statement to make sure that it works, that compares the test value to the value returned from the constant with a fault tolerance of 0.0. But of course, I don't have this implementation, but Eclipse can help me here. And the tip that is on the left-hand side on the bar, I can use that to create an interface that is the expression that I'm missing in the test. Eclipse will initiate the wizard with the correct values, except I don't want it in the package test, so I'm going to go up one package. Now that we have the expression interface, we can go back to the test class and fix some of the other errors. I'll first add the getValue method to the expression and change the return type to double. As I go back to the unit test, I see that I also need to create the class constant. Just fix the package declaration and we should be good to go. So that created a class. Now let's go back to the unit test and see what else we need. We need the constructor that takes the value. Test value is not a good name here, so I'm going to use value. And then I'm going to use a little trick in Eclipse, just say this value equals value, and then let Eclipse create the field for me. Finally, we need to fix the getValue method and make sure we return the value passed in the constructor. And now we can get rid of the final error in the test class. We need to basically statically import assert, so I can write just simply assert and not assert equals. It's just a little shortcut. Then let's finally run the unit test and make sure that it works. And yes, we get all green and everything looks good. So we now have a constant. So let's go on to a more complex implementation. Let's create the adder. Here we should be able to create a couple of test values. Let's say 2.0, 4.0, and then we should be able to create the expression. However, the adder should take expressions as parameters. So we need to wrap these test values into a couple of constants, call them left and right. So they add up the left and right. And then all we need to do is to write the assert statement. The assert statement should compare the test value A plus test value B and the value from the object under test, E in this case, so E.getValue. And the tolerance we should be able to do simply 0.0. Again, I took the approach where I wrote the unit test before I had implemented the adder, so of course we have an error on the line where we create the adder. I'll use Eclipse again to create the adder class and put it one below the test package, so in com.scibike.composite. Now the adder class needs a constructor that takes two expressions, the left and the right. And I can use the trick again by saying this.left equals left and this.right equals right. And then use Eclipse to construct the two fields. That's just, again, a shortcut. And finally, we need to fix the getValue method. And all that should do is to go and grab the left value and then add that to the value from the right-hand side and return it. So we can now try to save the file and run the unit test again and see if it all works. And it looks good. Everything is green. Our tests are passing. Now let's create this test for the subtractor, and I can simply copy the adder and fix it. So I'm going to rename it to test subtractor. Instead of creating an adder, I'll create the subtractor. And then of course I need to test it against a subtraction of test value A and test value B. This time it makes more sense to copy the adder to create the subtractor instead of using the quick fix. And I can do that by simply dragging the adder onto the package. That will make a copy. I'll rename it and I'm going to call that class subtractor. I'll open up the subtractor file. And really all I need to do to this is to change the sign. So change the plus to a minus and we should be done. In the test class, I will have to import the subtractor and then we should be able to run it. When we run the unit test again, we see that we now have 3 tests and they all succeeded, all green. So what we did with the adder and the subtractors, we did a copy and paste. Whenever I do that in Java, I feel like I'm missing some common abstraction. So I'm going to introduce a common abstraction for all the binary expression, adder, subtractors, divider, and a multiplier also. I'm going to select the expression and then create a class that I'm going to call binary expression, and that implements the expression interface. This new class, binary expression, we need a constructor to take the left side and the right side. And I'll use the same trick as we used before by writing this dot left equals left and this dot right equals right. And I also need to remove this implementation because we don't know how to get the value at this level of abstraction. We'll add the two fields and make sure that the class is declared as abstract since it doesn't implement the getValue method. I'm just going to make it simple here and make these fields protected. Now that we created this common abstraction for complex expressions, we can now refactor the adder and the subtractor. I'll start with the adder and I'll make it extend binary expression instead. We don't want to have the fields ourselves since they're on the base class. So I'll change the constructor to simply call the superclass constructor. And then we can remove the left and right side. And that should do it for the adder. Then we'll make the equivalent changes to the subtractor also. Well, we made the adder and the subtractor a little bit simpler by introducing binary expression. I'll launch the test and make sure it all works. And it looks like it does. Everything is green and we're good to go. It should be very easy for us now to create the divider and the multiplier. All we need to do is to simply drag the adder and create the divider. And the divider, we need to change the sign to use divider instead of the plus. And we can do the same thing with the multiplier. Just open it up and then change the sign here to a multiplication. And we should now have the 4 basic operators. Let's finish up some tests also, so we have tests for all the operators. We should be able to copy the existing test for subtractor. Just make it for the divider first and make sure we divide. And then we should make another one for the multiplier and of course replace the operator with a multiplier. And then we can try to run it and take a look. Oops, I did not attach a test tag. So we'll have to do that. Put the two tests together and I see I have an error again. Let's see what I did now. Okay, so I forgot to change the subtractor out to create new dividers and multipliers instead of keeping the subtractor. So we'll do those changes too. We'll see if it works. And with that, I think we completed up the framework. So let's take a quick look at what we're doing in drawings. Let's assume we have a fairly complex expression, something like this. 3 plus 5 multiplied by 100 divided by 2 plus 64, for instance. Now, what exactly would that look like as an instantiated object graph? Using our implementation, this expression will form a tree structure where the root object will be the divider. This is simply because the divider is the expression that has to be executed last after whatever is above the divider and below the divider has been calculated. On the left side of the divider, we have a multiplier. The multiplier has on its left side a plus or an adder. The plus has on its left side a 3 or the constant 3, and then on its right side the constant 5. Going back up to the multiplier, it has on its right side the number 100 or the constant 100. The root divider has on its right side a plus, and that plus or adder has on its left side a 2, and then on its right side the number 64. So using the class structure that we have now, we should be able to instantiate this object graph. And what's interesting after that is exactly how do we evaluate this expression, or how do we calculate? And this is one of the big powers of the composite structure in object-oriented software, because every object can have a method, and we can actually use delegation through the tree structure to execute the behavior that we want. So for example, if we were to ask plus what its value is, it wouldn't know by itself, but it could delegate to its left side where it finds 3, and then from its right side where it finds 5, and then say my value is 8. The multiply would take its left side, which is the plus, and find that its value is 8 times its right side, which is 100, and get to the value 800. The right-hand side of the divider's plus will find its value to be 66. Finally, we get to the divide, which by delegating to the multiply found 800, delegate to the plus, got 66, and we'll then divide 800 by 66. 66 go into 800 12 times. 12 times 66 is 792. That leaves us 8. So we should get something like 12 and 8 over 66, which is 12 over 4 over 33. So that would be 12.4 over 33. That would be 0.12121212. Try this out in code. Let's create a test case for that. I'll just call the test case for test complex expression, and then we'll construct an expression E. The example I drew had at the root a divider, and the divider had on its left side a multiplier. That multiplier had on its left side a adder with two constants. One was 3.0 and the right side was a constant 5.0. The multiplier had on its right side a constant which we said was 100. That completes the multiplier, so we just have to finish up the right side of the divider, which was an adder, which added two constant, 2.0 and 64.0. Let's see, we just get the parentheses right here. I think that completes the expression actually. So now all we need is an assert. Now we calculated while we were doing the drawing that the result of this expression should be 12.1212121212 and so on. So we need to write an assert that checks that. So we'll create assert equals 12.12121212. Don't need to fill it all out. And then we compare that to the expression's value. And I'll just put a reasonable fault tolerance here. Then all we need to do is to run the unit test and see if we get the right values, and we did. So we now have implemented a fairly complex example of a composite, the example being this expression framework. I've showed you the composite pattern. It is one of the most applied patterns. In fact, when I interview object-oriented designers that applied for work with my company, I always give them problems to solve where the composite pattern can be used. That is a showstopper for me if a candidate does not know the composite pattern. The composite pattern is a way of organizing objects into structure. The most common structure is a tree, but we occasionally also use the pattern to build more complex structures in general. The pattern is easily recognized when viewing a design in a class diagram. You will see the characteristic loop that spans inheritance, but also associations. The inheritance is used to capture the commonality between the leaf and the composite. We often organize, or we call that root concept and component in the pattern. The association is there to allow for the organization of objects. With that, we conclude this session on composite. We'll see you for the next pattern.